Hello everyone, and welcome back. Today we're going to be continuing our exploration of multivariable calculus and discuss the tangent line extension in the multivariable realm. So let's sort of review what we meant by, the tangent line to a curve for a single variable function. So let's assume that we have this smooth curve f, and let's assume that we're interested in a particular point here. So this would be, for example, x, and let's assume that this is its associated y value. And let's assume that we're interested in finding the tangent line to this curve at that point. So obviously we would find the derivative at that point, and that would be the slope of the curve at that point. And then in order to find the intercept of that line, then you just need to use that point in order to get that vertical intercept value. So this line is usually referred to as the tangent line to f at the point x comma y, right? So that's our tangent line, and we also sometimes find another point or line or vector, and that's usually the line or vector that's orthogonal or perpendicular to that tangent line. Some people call this the normal line, and some people call a vector the normal vector to that line, which could go in either direction. So that's what we had in the single variable world, and now let's sort of discuss what we're going to do in the multivariable world. So now we're going to have two inputs, x and y, and then we're going to have an output, say f of xy, and then we're going to have some surface. So let's assume that we have some contours here, and let's assume that this sort of curve is like a mountain in these particular dimensions. Right? So let's assume that that is our little mountain. So let's assume that this point here is our point of interest. So that's an x, a y, and a z. And what we're going to be looking for, instead of a tangent line, we're going to be looking for a tangent plane to that particular point. Right? So that would be a tangent plane. Tangent plane. And from that tangent plane, we will then get a normal vector that is orthogonal to that particular plane, right? So that would be our normal vector, right? And of course it would go in the opposite direction as well. So that's what we're going to be going for. And again, why do we actually care about tangent lines in tangent planes? So keep in mind, if you remember anything about Taylor series for functions, tangent lines as well as tangent planes will be, or they serve, as linear approximations to functions around a given point. Around a given point. Because if we look at this particular function graphed in blue, if we look really, really close to this curve in some neighborhood, let's assume this little box here, the line is practically equal to the values given in dark blue. And the same can be said about the tangent plane in green around that surface in blue and light green. Okay, so let's just go over how we found tangent lines for single variable functions. So let's look at a brief example. Let's assume that we have a very basic function f of x is equal to 5x squared minus 2x plus 1, whose function value, say at 2, is equal to 17. So if we find the derivative of this function, which is actually very trivial, that's going to be 10x minus 2, and we can find the slope of the curve at 2, and that's going to be equal to 20 minus 2, that's going to be equal to 18. So we have a point to 17, we have the slope, which is going to be equal to 18, and then we can find the tangent line to the curve at this particular point. And keep in mind what we're doing here is we have some parabola here, and it has some curve, and we have some point over here, let's say at 2, and we're interested in finding this particular line here, right, the tangent line. So the tangent line, or the linear approximation to the curve at this particular point x, is going to be equal to, so that's going to be equal to 18x, and one can show that the intercept of this particular line that passes through 217 has a slope of 18. That intercept is just going to be equal to minus 19. All right, so that is the linear approximation to this particular curve. And now let's assume that we're interested in finding a normal vector in either direction, regardless of the length, because there's actually infinitely many normal vectors. Whichever vector we choose, let's call this normal vector Vm, the dot product of that vector, and keep in mind this vector is dictated by the slope of that line, and keep in mind the slope of this line is equal to 18 over 1, so rise over run. So the x component will be 1, and the y component will be 18, so it just needs to dot product with this vector 1, 18, and the dot product must equal to 0 in order for these to be orthogonal or perpendicular to one another. So there's obviously infinitely many choices you could choose. For example, we could choose Vn is equal to minus 18, 1. Just switch these components around and negate one of them. Or you could choose, for example, Vn to be equal to 18 minus 1. Right? And of course you can scale these to any scalar value that you want, but generally speaking the normal vector would be any constant multiple times 18 minus 1. And obviously c should be equal to a constant, and obviously the constant should not be 0. Right? So that's how we find tangent lines and normal vectors for single variable functions. Okay? So let's just review just a couple other things. So keep in mind in R2, if we have this line, f of x is equal to mx plus b, the partial derivative of f with respect to x will be equal to equivalent notation of fx of x. This is going to be equal to m. Right? And keep in mind this is at any particular x, so it's a constant function. So for example, fx at say x0 will be equal to m, and that's obviously going to be true for any x0 and the associated domain of that function as well. True? So if f of x0 is equal to y0 for some function f of x is equal to y, then what we're going to have is y minus y0 divided by x minus x0. This will be equal to fx at x0, because this is the slope of the curve at a particular point. Right? So if we have this particular relation, then obviously we can rearrange this to get y minus y0 is equal to fx of x0 times x minus x0. And keep in mind what motivates this particular structure is that fx is equal to the partial derivative of f, which in this case is y, divided by the differential of x. Okay? So this equation here always gives you the equation of the line tangent to f at the point x0, y0. And that's very, very important. So if we want to build the equation of the tangent plane to f at a particular 3 input value, what type of structure would that follow? So similarly, in R3, and also R4, R5, and up to Rm, so now we're going to say that fx0, y0 will be equal to z0. If we follow the same exact parallel structure, and you can actually prove this in a similar way as we did in the two-dimensional case, and I'll leave that for you. So we're going to have z minus z0 will be equal to fx at x0, y0 times x minus x0 plus f of y, x0, y0 times y minus y0. Right? And that will be your primary structure. So what is this the equation of? So this is the equation of the plane tangent to f at the point x0, y0, z0. right? So that's actually quite nice. So let's go through a numerical example just to see how this works, and then we're going to go into how we can find the vector that is normal to this particular plane using methods that we've previously discussed. For our example, let's assume that f of xy is equal to 3x squared plus 2xy plus y cubed. And let's assume that we're interested in constructing the equation of the tangent plane when x0, y0 is equal to 1, 2 respectively. So the first thing that we need to do is figure out what is the corresponding z value for this particular two-dimensional input. So if we input 1 and 2, we're going to have 3 times 1 squared, and then plus 2 times 1 times 2, and then we're going to have 2 cubed. So we're going to have 3 plus 4 plus 8, and that's going to give us 15. So that's the associated z0 value. So that means the point of our interest is going to be equal to 1, 2, 15. Now we need to construct the partial derivatives fx and fy at this particular point 1, 2. So let's do that. So the partial derivative with respect to x of xy, so that means y is going to be held constant. So the derivative of 3x squared is going to give you 6x. The derivative of 2xy with respect to x is just going to be equal to 2y. And the derivative of y cubed will be equal to 0 with respect to x since there's no x's there. So that's going to give us what? So that means fx at 1, 2 will be equal to 6 plus 4, and that's going to give us 10. Let's do the same for fy. So fy of xy is going to be equal to the partial derivative with respect to y, so 3x squared is a constant. We're going to have, what is that going to be? That's going to be 2x, and the derivative of y cubed, that's going to be equal to 3y squared. And then we're going to have fy of 1, 2, and that will be equal to, well, so 2 times 1 will be equal to 2, plus 2 squared is going to be 4, times 3 is 12, so 12 plus 2 is going to give us 14. Once we have those values, now we can construct the equation of our tangent plane. So, using the formula that we built before, that's going to give us what? So z minus z0, that's going to be equal to 15, is equal to the x gradient, which is going to be equal to 10, times x minus x0, which is 1, plus the y gradient, which is going to be 14, times y minus the y0 value, which is going to be equal to 2. Once we have that, we can technically present this as our answer, but I just want to clean this up a little bit more and write it in functional form. So let's distribute that 10, let's distribute that 14, let's combine like terms and see what we get. So we're going to have 10x minus 10 plus 14y minus 28, and that's going to be z minus 15. And let's isolate this equation for z. So z is going to be equal to 10x plus 14y, and then we're going to have minus 28 minus 10 minus 15, so that's going to be equal to, what is that going to come out to? So that's going to be equal to minus 38 plus 15, and I believe that's going to be equal to, what is that? That's going to be minus 23. So we have our linear approximation around that point. So we're going to write it L x, y, so our linear approximation will be equal to 10x plus 14y minus 23. Right? So that's the equation of our tangent plane. So keep in mind that L, evaluated at our point of reference, which in this case was 1, 2, should be equal to 15. So let's see if that's true, just to make sure this is potentially correct. So that's going to be equal to 10 times 1 plus 14 times 2 minus 23, and you should be able to verify that that is indeed equal to 15. Right? So as long as xy is near 1, 2, then this will give you a relatively decent approximation to the original function that we were analyzing. So for example, point of reference you could do, for example, would be 1.1 comma 1.9. So 0.1 to the right of x and 0.1 to the left of y. So if we plug this in, that's going to give us 10 times 1.1 plus 14 times 1.9 minus 23. And that's going to come out to 14.6. And if you actually do the exact value, which is going to be f of 1.1 and 1.9, you're actually going to get 14.669. So at least for this particular point, they are actually relatively close to one another, right? But keep in mind, the farther and farther you get away from 1, 2, the larger and larger the error can potentially become, right? So for the general arbitrary function, if we want to see what a linear approximation would look like, we would have, for example, fxy, and this would be equal to fx0, y0. So some people will usually say that this is a 0th order approximation, because obviously if you're not equal to exactly x0, y0, then fxy could be very, very different, right? Because this assumes that f is practically a constant. But what we would do is we would add more terms to this approximation. So fx x0, y0 times x minus x0, and then fy at x0, y0 times y minus y0. And what is this? Well, keep in mind, this is just a different way of saying z0. So what we have here in disguise, so this is actually what we refer to as the first order approximation to that particular function centered at x0, y0, right? And you may be like, oh, that actually kind of looks like a Taylor series that's being about to build, right? Because there should be other terms here, in particular some O term that depends on the distance from x and the distance from h. Because keep in mind, if we look at a particular x value in 1 dimensions, that's going to be equal to f of x0 plus f prime of x0 times h all over 1 factorial plus, h squared over 2 factorial times f double prime of x0 plus some other stuff, right? It's just that we don't exactly know what this is in the 2-dimensional realm. And keep in mind, this h is just the distance x is from x0, right? Because that's technically h x in disguise, and that's technically h y in disguise. But we'll get into Taylor series a little bit later. But before we get too far from our current example, let's try and find the equation for the vector that is normal to the plane for the function that we've already built. So now that we have the equation of our tangent plane, now let's see if we can figure out a vector that is normal to that particular plane at that particular point. So we have our tangent plane, 10x plus 14y minus 23, and our point of reference p0, 1, 2, 15. So what are we going to build? So let's assume that this picture corresponds to our linear tangent plane approximation. This is a plane in higher dimensional space. And let's assume that this point here corresponds to our p0. And what we need to do is figure out the equation of the vector that is orthogonal at that point. So if we were to construct 2 other directions, let's assume that we have this vector here and that vector there, it should create right angles with respect to that one, and it should create a right angle with respect to the other one, right? So it's a right angle in 2 directions, the x and the y. Now, let's assume that this point here actually corresponds to P1. Let's assume that this point here corresponds to P2. So what we're going to do is we're going to find these points P1 and P2 that all belong to our plane, right? Now, some requirements about these particular points: they cannot be collinear. So that's the first requirement. And the second is they must all be in our plane. Now our plane was built on P0, so P0 by default will always be in our plane. So it's actually up to you to figure out what P1 and P2 can be. And as a little side note, there are infinitely points P1 and P2 because I can go a little bit more into the future of P1, I can go a little bit more into the future of P2. I can also work backwards in these directions as well, and if you want to be fancy, you can actually go in any diagonal direction as well, as long as it's defined there. So what I like to do personally is sort of increment my x values by 1, and increment my y values by 1, and keep everything else fixed. So for example, for P1, if I sort of stay consistent with my picture, it looks like I've incremented my y by some value. So I'm going to increment my x by 1, or increment my x by 0, and increment by y by 1, and then we're going to have some associated z value because it's not necessarily a flat tangent plane. And then for P2, we're going to increment our x, keep our y value the same, and then we're going to have some associated z value. So you're going to take these values, 1, 3, and put them in, and then do 10 times 1 plus 14 times 3 and subtract 23, and then you're going to get some value, and in this case you're going to get 29. And similar for your P2 that you've selected, 10 times 2 plus 14 times 2 minus 23, you're going to get some value here, and in this case for this particular point, this is 25. So of course I leave it to you to verify that these points are not collinear and all of them are in your plane. Right? So as long as you verify those points, then these points are perfectly okay. So now what I want to do is I want to figure out these vectors that I have built. So for example, this is P0, and then we're going to have a vector from P0 to P1, and then another vector from P0 to P2. So I'm going to call this vector here, I'm going to call this vector u, and then we're going to have this vector here, then we're going to call this v. And then from u and v, we're going to find this normal vector, which I'm going to call n, that is perpendicular to both u and v. That is n dot product u is equal to 0, and n dot product v will also be equal to 0. Again, there's infinitely many ones, but they're all scalar multiples of each other. So how are we going to build this vector u and this vector v? So we've done this a little bit before, but let's just review how to do it. So u will be equal to the vectorized version of P1 minus the vectorized version of P0. So that's going to be equal to 1, 3, 29 minus our reference point 1, 2, 15. And then v will be equal to the vectorized point of P2 minus the vectorized version of 0. So that's going to be equal to our 2, 2, 25 minus a reference point 1, 2, 15. And then you're going to have your vectors u and v. So that's going to be equal to 0, 1, 14, and 1, 0, 10. All right, so those are your u's, and those are your v's. Okay? So remember, if n is defined to be equal to the cross product between u and v, then n dot product u will be equal to 0, and n dot product v will be equal to 0. So the cross product always gives you a vector in 3 dimensions that is perpendicular to both u and v. So remember, how do you find cross products? So n, this vector, will be equal to the determinant of the ijk component 3x3 matrix, and then we're going to have u on one row, and then v on another row. So that's going to be equal to the determinant of I, j, k, and then u, 0, 1, 14, and then 1, 0, 10. Right? Let's expand across row 1 to sort of figure out what this determinant will be. So we're going to have n is equal to, so we're going to have I times the determinant of the associated subminor matrix. So that's going to be 10 minus 0. And then we're going to have minus j. And then we're going to have the determinant of that submatrix. So 0 times 10 is 0, minus 14 times 1 is 14. And then we're going to have k, and then 0 times 0 is 0, minus 1 times 1 is 1. So that's going to give us that. So this is going to be equal to 10i plus 14j, and then we're going to have minus 1k. And if we write that in vector form, we have that the normal vector will be equal to 10, 14, minus 1. So that's our normal vector. And keep in mind that our tangent plane, LTX, was equal to 10x plus 14y minus 23. And also keep in mind the reference point for which this is approximated to. Our reference point for this was 1, 2, 15. And that is how you can find equations of tangent planes and also normal vectors in 3 dimensions. Hope you enjoyed this video, and I'll see you in the next one. Take care.